Imagine drifting through intergalactic space, far from any star, far from the soft glow of spiral arms or the reassuring density of the cosmic web, and entering a region so empty that for millions of years nothing might pass close enough to cast even the faintest shadow. This is where we begin. Inside a cosmic cavity nearly 330 million light-years wide, a hollow carved into the structure of the universe itself, a place astronomers call the Boötes Void. Out here, the nearest galaxy might be tens of millions of light-years away. The intergalactic medium is so thin, it borders on metaphysical, a handful of atoms drifting in each cubic meter. There is a silence that cannot be heard, only understood. A silence built not from stillness, but from a lack of witnesses. As you float here, there's a strange shift in perspective. Human senses are built for closeness, for rooms, forests, cities, even oceans. Our imaginations are comfortable with large, but not with this. Here, scale becomes disorienting. You look around and see almost nothing. A few pin-like galaxies flickering at impossible distances. Specks of light isolated so fiercely that each one feels like a secret the universe forgot to share. And the strangest part is this. This emptiness is not a mistake. It's a physical feature of the universe. Cosmologists describe emptiness not with metaphors, but with numbers. The average density of matter in the universe, dark matter, baryonic matter, everything, is a delicate balance sculpted by the physics of the early cosmos. In a region like the Boötes Void, that density collapses to less than 10% of the norm. To a physicist, this difference is captured in a deceptively simple variable, the density contrast, written as delta. In the Boötes Void, delta is roughly minus 0.9. That means this place contains only about 1/10 the matter it should. To put that in more human terms, if the universe were a city, the Boötes Void would be the quietest, most abandoned district imaginable, sprawling for hundreds of millions of blocks, with only a handful of houses still standing. But there's something beautiful about this emptiness too, a clarity, the sense that you're floating inside the universe's own breath between words. Before we go deeper into the physics, the puzzles, the measurements that revealed this sprawling hollowness, if you enjoy exploring quiet cosmic mysteries like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow and it keeps these journeys alive. Now, anchored here in the calm of the void, the scientific picture begins to take shape. What does emptiness really mean at this scale? We often imagine the universe as a smooth, evenly spread ocean of galaxies, but the truth is more intricate, more architectural. Galaxies cluster into filaments and walls. Between them stretch the cosmic voids, regions where gravity didn't gather enough matter to build anything substantial. The Boötes Void is one of the most extreme examples. A super void. Not entirely empty, but astonishingly underdense. When astronomers first encountered it in the 1980s, the reaction was something between awe and confusion. A sphere nearly 330 million light-years across with almost nothing inside. It seemed too large, too empty, too improbable. But as our cosmic maps improved, it became clear that this wasn't a cosmic error. It was a natural consequence of how the universe grew from tiny, quantum-seeded fluctuations. Still, numbers alone can't fully capture the psychological weight of a place like this. Humans evolved in a world where the horizon was never more than a few kilometers away, and where survival depended on noticing movement, sound, and the presence of others. Emptiness, to us, often signals danger or loneliness. But in cosmology, emptiness is structure, it has rules, it has dynamics. It expands faster than denser regions, pulled outward by its own lack of gravity. It shapes the surrounding universe, pushing matter into walls and clusters like water flowing around stones. Inside the Boötes Void, you are drifting through a place where structure never fully formed, a region that has been stretching slowly since long before Earth existed. if you could watch this void on fast forward over billions of years, you'd see it inflate like a bubble in dough, pushing galaxies and dark matter toward its edges, making the filaments around it thicker and brighter. But standing here, if standing is even the right word, the void feels frozen, quiet, eternal. The temperatures are just a few degrees above absolute zero. Photons from the cosmic microwave background glide past you, faint and ancient. The nearest star's light might take hundreds of millions of years to reach your eyes. And yet, even here in the vastest emptiness near us, there is still something. A few lonely galaxies suspended like lanterns, each one a tiny island of complexity surrounded by an ocean of almost nothing. These galaxies are unusual, often bluer, star-forming, isolated, shaped by lives without neighbours. They are the rare inhabitants of a space that seems determined to remain empty. As you look around, the void almost feels like a cosmic meditation, a reminder that not all parts of the universe are crowded with stars and drama. Some regions are defined by absence, by silence, by the gentle physics of underdensity. And the question that lingers naturally is, how does something this large and this empty come to exist? To answer that, we'll step back into history, into the story of how astronomers first stumbled upon this hole in the universe, and why it changed our understanding of cosmic structure forever. When we talk about the discovery of the Boötes Void, it's tempting to imagine some dramatic moment, an astronomer staring at a screen, blinking in confusion as a massive cosmic cavity unfolds in front of them. But the real story began long before anyone realized a hole was there at all. It started with a shift in how scientists thought about the universe, from looking at objects to mapping the structure between them. By the early 1970s, astronomers were collecting redshifts in growing numbers, measuring how galaxies stretched away from us as the universe expanded. But these measurements weren't just about distance. They were about creating a three-dimensional map of the cosmos. Until then, humanity had only a two-dimensional understanding of the sky, like trying to guess the shape of a forest by looking at treetops on the horizon. Redshift surveys changed that. They let astronomers place galaxies not just on the sky, but inside space. And that is where the story really begins, with a team of scientists who would later be nicknamed the Seven Samurai. Their core members included Robert Kirshner, Augustus Oehmler, and Paul Schechter, names that would become central to the study of cosmic large-scale structure. The group wasn't searching for a void. They were searching for patterns. They wanted to understand how galaxies moved, why some regions were crowded and others sparse, and what these motions said about the dark matter beneath everything. At the same time, a major survey was taking shape at the Harvard-Smithsonian Center for Astrophysics, the CFA Redshift Survey. It was one of the first attempts to systematically measure galaxy redshifts over a large patch of the sky, converting the sky from a flat backdrop into a cosmic landscape. The technique was simple in concept, but revolutionary in consequence. You measure the light from a galaxy, identify how much its spectral lines are shifted, and from that calculate its distance. One point at a time, the universe becomes a map. In the mid-1980s, when the CFA team started assembling the first slices of their survey, the universe began revealing itself in a way that no photograph could match. Filaments appeared, long strands of galaxies stretching across tens of millions of light years. Walls formed, vast sheets of matter that cut through cosmic space like glowing continental plates. Clustered knots materialized where gravity had woven the densest structures. But between these bright threads of the cosmic web, the maps also revealed darkness, empty spaces, cavities, and then one cavity that simply didn't make sense. It emerged in the constellation of Boötes, a region that, for observers on Earth, looks fairly ordinary, but when astronomers plotted the redshift data in 3 dimensions, they saw something breathtaking, a massive sphere of nearly empty space, a region where galaxies should have appeared, hundreds, maybe thousands of them, but simply didn't. The void was so large that the team initially questioned their methods. data that extreme usually signals a technical problem, not a cosmological one. But the numbers held. Galaxy after galaxy was plotted, and still a vast hollow remained. It wasn't a statistical fluctuation, it wasn't a gap in observations, it was real. A region with a radius of roughly 165 megaparsecs, or about 330 million light-years across. To put that into human language, if the Milky Way sat at the center of such a void, the nearest large galaxy would be so far away that the entire history of human civilization wouldn't be enough time for its light to reach us. The sheer scale was disorienting. Most known cosmic voids were tens of millions of light-years wide, not hundreds. The volume of this one was estimated at around 10 to the 17th cubic light-years, a number so large that it barely registers as meaningful without context. It was like discovering that the universe contained not just valleys between its cosmic mountains, but entire oceans of emptiness. Kirshner later described the team's reaction as a mixture of disbelief and delight. The Boötes Void was too big, too empty, too unexpected. It forced astronomers to confront the possibility that large-scale structure in the universe was far more extreme than anyone had predicted. But the surprise didn't end with size. When the team searched for galaxies inside the void, they found almost nothing. A handful here and there, scattered sparsely through the dark. Ultimately, fewer than 70 galaxies would be identified within its vast interior. For comparison, a similarly sized region in a typical part of the universe might contain thousands. Even stranger, the galaxies inside the void seemed unusually isolated, sometimes younger or more actively star-forming, as if shaped by an entirely different evolutionary environment. But that realization would come later. In the 1980s, the mere existence of such a structure was enough to shake cosmology. And this was happening at a time when the cosmic web was only beginning to emerge as a concept. The CFA slice of the universe images, those wedge-shaped diagrams that revealed filaments and voids, were among the first visual proofs that the universe wasn't a uniform sea of galaxies. Instead, it was a foam-like network, with dense intersections and cavernous gaps. The Boötes Void was the most dramatic of these gaps, a kind of cosmic exclamation mark. The discovery also sparked debates. Some wondered whether such a void was compatible with the standard cosmological model. Others speculated whether the void might indicate new physics, exotic forms of dark matter, unusual initial conditions, or deviations from the expected distribution of density fluctuations. Most of these concerns faded as simulations improved and showed that supervoids were rare but expected, but in the moment the void felt almost too big to be real. And yet, it was real. It still is. A reminder that even with billions of galaxies, even with cosmic structures stretching across unimaginable distances, the universe is still mostly made of space. Empty, silent, cold, expanding. The Boötes Void was a revelation not because it contradicted cosmology, but because it highlighted just how dramatic structure can become when left to gravity and time. It was a signpost that the universe had not grown uniformly, it had grown wildly, carving out hollows and weaving dense walls around them. And with that discovery, astronomy entered a new phase, one focused not just on stars and galaxies, but on the vast, seemingly empty regions that shape them. Next, the question becomes, what exactly is a void, physically? How do these enormous hollows form in the first place? The Boötes Void didn't appear out of nowhere. It wasn't carved out, hollowed, or blown open. It grew, slowly, subtly, guided by the same physics that shaped the entire cosmic web. To understand why such immense hollows exist, we have to step back to the earliest moments of the universe, when everything that would later become galaxies, clusters, and voids was still compressed into a nearly uniform sea of primordial plasma. At first glance, the infant universe looked smooth. The cosmic microwave background, the faint afterglow of the Big Bang. reveals temperature variations of only about 1 part in 100,000. Those tiny fluctuations may seem insignificant, but they were the seeds of structure. Slightly denser regions contained a little more matter. Slightly emptier regions contained a little less. And under gravity, that difference is everything. If a region started its life a bit denser than average, it would attract more matter, grow even denser, and eventually collapse into galaxies and clusters. And if a region started slightly emptier, just a fraction below the average density, it would lag behind in growth, expand a little faster, and gradually become a cosmic void. Over billions of years, these small differences amplified until the universe developed a stark architecture, filaments and walls of galaxies surrounding enormous underdense cavities. One of the simplest descriptions of how this structure emerged is the Zeldovich approximation, proposed in 1970 by Soviet physicist Yakov Zeldovich. It's a method for predicting how matter flows in the universe as it evolves. The idea isn't complex in form, but it paints a remarkably accurate picture. Imagine a balloon covered with tiny dots. As the balloon expands, the dots move farther apart, but their movement isn't uniform. Some regions stretch more than others, depending on the subtle gravitational pushes and pulls created by the early density field. In the Zeldovich approximation, matter streams away from underdense regions along straight trajectories, while collapsing into denser regions along preferred directions. Filaments form where matter collapses along two directions, leaving one dimension elongated. Sheets or walls form where the collapse occurs along one direction. Between these structures sit the voids, areas that experience what is essentially gravitational evacuation. These early fluctuations were themselves set by cosmic inflation, the brief but staggeringly rapid expansion believed to have occurred a tiny fraction of a second after the Big Bang. Inflation stretched quantum fluctuations, minute differences in energy density across astronomical scales. When inflation ended, those fluctuations became the blueprint for structure. The densest patches would later form galaxy clusters. The emptiest would become voids, including giants like the Boötes Void. So what distinguishes a void from any random underdense region? Cosmologists classify voids by comparing their density to the cosmic average. If you take a large volume of space and find that it contains far less matter than expected, you can describe the contrast using a value called delta. It's defined as delta equals density minus average density divided by average density. If delta was zero everywhere, the universe would be perfectly smooth. If delta is positive, the region is overdense. If delta is negative, the region is underdense. Voids typically have density contrasts around delta, approximately minus 0.8, meaning they hold only about 20% of the matter expected. But the Boötes Void is even more extreme. Its delta is closer to minus 0.9. That means it contains only about 10% of the matter that should be there. Interestingly, the physics of underdensity leads to a counterintuitive effect. Voids expand faster than the rest of the universe. Because they have less mass, they exert less gravitational pull. The surrounding regions, being denser, pull matter toward themselves, and the void effectively empties out, pushing galaxies toward its edges. Over time, this accelerated expansion stretches the void even larger. If you could see this process unfold over billions of years, the center of a void would become emptier and emptier, while the boundaries, where outflowing matter accumulates, would grow into walls or filaments. This is why voids tend to sit between some of the most dramatic structures in the universe. Their emptiness is not passive. It actively shapes what forms around them. Another crucial concept in the formation of voids is shell crossing. In an overdense region, matter collapses inward. In a void, the opposite happens. Matter flows outward. As the void expands, the innermost shells of matter outrun the outer shells. Eventually, these shells cross over each other, creating a thin region of higher density at the void's boundary. This boundary is where galaxies, filaments, and clusters gather. marking the void like a faint cosmic outline. Shell crossing is what stabilizes a void. Once it occurs, the void becomes a coherent, recognizable structure, a true bubble in the cosmic web. Its interior becomes extremely sparse, while a ridge of denser material marks its edge. The Boötes Void almost certainly underwent this evolution long before the first galaxies formed. The remarkable size of the Boötes Void isn't the result of a single underdensity. Simulations suggest that large voids form when several smaller voids merge over cosmic time. Think of bubbles merging in a foam. The boundaries dissolve, the cavities unite, and a single vast hollow emerges. What makes the Boötes Void extraordinary is the scale of this merging, a process that required billions of years and a remarkably quiet patch of cosmic initial conditions. And yet, even within this emptiness, galaxies exist. They are few, but they are there, lonely, almost adrift. Their existence proves that the void isn't a perfect vacuum. It's simply a place where the gravitational tides favored expansion rather than collapse. Understanding voids isn't just about filling in the map of the universe. These vast, underdense regions provide sensitive tests for dark energy and gravity. Because voids expand faster than average, they amplify the effects of cosmic acceleration. Their shapes and growth rates help cosmologists test competing theories of gravity and measure the universe's expansion history. In many ways, voids are laboratories more useful than clusters. They are simpler, quieter, and less chaotic. And so, when we look at the Boötes Void, we're not just staring into a cosmic absence, we're looking at a key part of the universe's architecture, shaped by the earliest fluctuations, governed by gravity, and driven by the expansion of space itself. It's a region where the universe expresses one of its most fundamental tendencies to amplify slight beginnings into vast, dramatic structure. When astronomers first confronted the Boötes Void in the early data of the 1980s, the picture was crude, a rough absence surrounded by scattered points of light. But as surveys became more sophisticated, the void began to sharpen into something far more complex than a simple empty sphere. It became a landscape, a three-dimensional structure that reveals its shape only when thousands of galaxies are pinned carefully in space using their redshifts as markers. Every new dataset added depth, like layers of fog clearing one after the other. One of the first steps toward understanding its structure came with expansive projects like the Sloan Digital Sky Survey, or SDSS, a mapping campaign that transformed cosmology. The SDSS telescope in New Mexico spent years capturing the spectra of galaxies across a third of the sky. Each spectrum carried with it a redshift, a stretching of light caused by the universe's expansion, which translated directly into distance. By combining the positions on the sky with redshift-based distances, SDSS produced immense three-dimensional maps showing where galaxies actually sit in space, not just how they appear on a flat, celestial dome. When SDSS swept through the region of Boötes, the void emerged with remarkable clarity. What had once looked like a vague hole in earlier surveys became a pronounced underdensity surrounded by intricate structure. And almost immediately, it became clear that the Boötes Void wasn't perfectly spherical. Its geometry is uneven, more like a slightly crushed ellipsoid, wider in some directions, narrower in others. Voids evolve dynamically, shaped by the mass distribution around them, and the Boötes Void carries the marks of these gravitational interactions. The void's asymmetry became even more evident when overlapping surveys were added into the mix. The 2DF Galaxy Redshift Survey, conducted with the Anglo-Australian Telescope, provided another powerful view. With more than 220,000 galaxy redshifts, 2DFGRS mapped southern sky regions with high precision, and even though it didn't center on Boötes, its data overlapped enough to refine its boundaries. The edges of the void brightened into clearer walls. Structures that had seemed smooth became webbed and irregular. Regions that looked empty revealed faint thread-like hints of galaxies. And then came DESI, the Dark Energy Spectroscopic Instrument, a modern survey designed to capture tens of millions of redshifts with incredible accuracy. While the Boötes region is only part of DESI's vast scope, the early data alone gives the void a new level of depth. With finer measures of galaxy positions and motions, DESI helps reveal substructures inside the void. Smaller voids nested within the larger one, like bubbles inside a bubble. This isn't unusual in cosmic architecture. Voids grow by merging, but remnants of their past shapes often linger as subtle density dips in their interiors. Inside the Boötes Void, astronomers have identified not just emptiness, but a layered topography of underdensity. Rather than being one smooth hollow, it contains multiple sub-voids connected by faint streams of matter. These thin structures, sometimes called tenuous galaxy strings or tendrils, are among the lightest threads of the cosmic web. A tendril might contain only a handful of galaxies stretched across tens of millions of light years, spaced so widely that each one could pass billions of years without interacting with another. These faint features are important. They show that even the most dramatic voids aren't absolute deserts. Gravity works everywhere, even in the universe's quietest neighborhoods, pulling what little matter exists into delicate configurations. The Boötes Void is extreme, but not disconnected from the broader web. Faint tunnels of structure tie it to the surrounding filaments like half-forgotten paths cutting across an abandoned landscape. When astronomers counted the galaxies inside the void, the number seemed almost absurd compared to its size. Across its estimated volume of roughly 10 to the 17th cubic light-years, only around 60 to 70 galaxies have been identified. In a typical region of that volume, thousands of galaxies would form a bright, textured field of clusters and groups. Here, those thousands are replaced by a mere few dozen, each shining in near-total isolation. The galaxies inside the void sit unevenly. A few cluster into minimal groups, but most stand alone, like solitary lanterns suspended in darkness. Some appear to trace faint lines, evidence of those tenuous strings, while others drift in what appears to be the void's true interior, far from any boundary. Void galaxies often have subtly unusual characteristics. They can be gas-rich, low metallicity, still actively forming stars despite their isolation. Without neighbouring galaxies to stir or strip them, they evolve slowly, almost leisurely, influenced by nothing except their own quiet gravity. To map all of this, cosmologists rely on redshift surveys not just as collections of distances, but as tools for revealing the shape of space. Each galaxy's redshift is like a point in a cosmic GPS system. Plot thousands of them, and the distribution of matter becomes a three-dimensional sculpture. Dense regions glow with countless overlapping points. Walls appear as curved surfaces of galactic light. Filaments snake through space as slender, luminous cords. And voids, especially one as immense as Boötes, stand out like cavities in a cosmic lattice. Redshift space itself, however, is not perfectly intuitive. Peculiar velocities, small gravitational motions on top of the universe's expansion, can stretch or compress structures along the line of sight. Massive clusters appear smeared into fingers, while voids can appear slightly elongated. But with enough galaxies and with surveys that cross-check each other's findings, the underlying geometry emerges cleanly. For Boötes, surveys from CFA, SDSS, 2DFGRS, and now DESI interlock like puzzle pieces, confirming its vast dimensions from multiple angles. One of the most visually striking ways to understand the void is through wedge diagrams, slices of the universe rendered as fan-shaped plots where each galaxy sits according to its direction and redshift. In these diagrams, the Boötes Void appears as a gigantic, empty bubble surrounded by a bright arc of galaxies forming its boundary. With each new survey, the arc becomes sharper, more detailed, more textured. Minor filaments extend from the walls into the interior like faint spider threads reaching into a cavern. Viewed this way, the void becomes something almost architectural, a hollow carved by gravitational evolution. Its edges show where matter pooled and collapsed into structures. Its interior reveals where the early density field dipped low enough for gravitational pulling power to fall behind cosmic expansion, letting the region swell and thin out. In some maps, the void looks nearly spherical. In others, slightly flattened. It depends on the slice, the survey coverage, and the orientation. But all views agree on one thing. This is one of the most dramatic and well-defined supervoids near us, a cosmological feature that takes shape not through human imagination, but through careful measurement and the patient gathering of millions of photons. And each survey adds depth. SDSS provided broad clarity. 2DFGRS added important cross-sections. DESI brings precision and internal structure. Together they reveal a void that is not merely an empty ball, but a layered architecture with sub-voids, strings of galaxies, and a complex boundary shaped by billions of years of cosmic evolution. Its interior density, its asymmetry, its faint structures, all of these emerging details turn a once surprising discovery into a richly understood region of the universe, one that continues to reveal its geometry with every new wave of observations. Galaxies inside the Boötes Void exist in an environment so different from the crowded cosmic web that they almost feel like natural experiments, isolated test tubes drifting in deep space. Their evolution unfolds without the usual pressures, encounters, or gravitational nudges that shape galaxies elsewhere. In the densest regions of the universe, galaxies constantly collide, merge, strip gas from each other, and exchange metals through winds and feedback. But inside a void, a galaxy may spend billions of years without meeting a single significant neighbour. Isolation becomes the dominant environmental force. This solitude shows up immediately in the chemistry of void galaxies. One of the clearest patterns astronomers have observed is their tendency to be metal-poor. In astronomy, metals are elements heavier than helium, produced inside stars and spread through galaxies when those stars die. In a typical environment, clusters, filaments, even average density regions, galaxies enrich each other. Gas flows between them. Supernova winds carry metals outward, and mergers mix stellar populations. Over time, this enhances the metallicity of the interstellar medium. Void galaxies don't participate in this cycle. Their isolation limits both inflow and exchange. Fresh gas from the intergalactic medium tends to be pristine, or nearly so, containing few heavy elements. With little interference from neighbours, this gas accumulates slowly. Star formation proceeds at a gentle pace, not the bursty, chaotic rhythm seen in more crowded regions. As a result, many void galaxies remain chemically young. Their metallicities lag behind the cosmic average, making them valuable for studying processes that mimic the early universe, where metals were scarce and gas was abundant. This low metallicity environment often goes hand in hand with another trait: ongoing star formation. It might seem paradoxical that galaxies in such lonely spaces are often busy forming new stars, but the explanation lies in gas content. Void galaxies frequently have large reservoirs of hydrogen, especially neutral hydrogen, known as Hi. This form of hydrogen emits radiation at a wavelength of 21 centimeters, about 8.27 inches, a signal that radio telescopes use to trace gas in galaxies. Hi surveys across void regions repeatedly show unusually high gas fractions in these galaxies. It's as if they've been saving fuel for billions of years, untouched by the stripping or consumption that companions would cause. The presence of abundant Hi is a crucial reason void galaxies can remain star-forming even when their metallicity is low. Heavy elements help cool gas, making star formation easier, but hydrogen-rich galaxies can still collapse into new stars if their gas is dense enough, or if internal processes like spiral waves or local instabilities compress it. Without outside interference, they can maintain stable, slow-burning star formation for very long timescales. These properties make void galaxies excellent laboratories for understanding the fundamentals of galaxy evolution. Many of the usual complicating factors drop away. No major mergers, no tidal interactions, no ram pressure stripping from cluster environments. Just the internal physics of gas, stars, and dark matter playing out in relative isolation. Observing them allows astronomers to see what galaxies might be like when left almost entirely to their own devices, evolving with minimal external influence. Among the galaxies in or near void-like environments, a few stand out as remarkable examples. One such object is SBS 1428+529, a compact, extremely low metallicity galaxy whose properties resemble those expected in the early universe. Its star formation rate is modest, but its chemical abundance is unusually low for its brightness and mass. Its position in a low-density region allows it to retain this primordial character. Galaxies like SBS 1428+529 show how voids can preserve rare evolutionary paths that are overwhelmed in denser environments. Another fascinating example, often cited when discussing void-like conditions, is DDO68, a small irregular galaxy with one of the lowest metallicities known in the nearby universe. Although technically not inside the Boötes Void, DDO68 occupies a similarly underdense region, making it a powerful analogue. Its stars and gas clouds reveal a system that has barely evolved chemically, despite forming stars over billions of years. In terms of metallicity, DDO68 is so primitive that it evokes comparisons to galaxies in the first billion years after the Big Bang. It illustrates how isolation can delay the usual enrichment cycle almost indefinitely, letting astronomers observe processes that are otherwise accessible only through extremely distant and faint objects. These examples highlight a broader theme. Environment matters profoundly in shaping galaxies, not just in how they look, but in how they form stars, how they rotate, how their gas behaves, and how their internal structures settle over time. One of the most intriguing pieces of evidence for this comes from deviations in the Tully-Fisher relation. The Tully-Fisher relation links the luminosity of a spiral galaxy to its rotation speed. In most environments, the relation is tight. Bright spirals rotate faster, faint spirals rotate slower, and the correlation is strong enough to serve as a distance indicator. But void galaxies sometimes deviate from this pattern. They can be fainter than expected for their rotation speed, or rotate more slowly than galaxies with similar brightness elsewhere. These deviations may stem from their unusual evolutionary histories. With fewer mergers, less external stirring, and long-lived gas reservoirs, the balance between dark matter, stars, and gas can develop differently. Even the shape of the dark matter halo, the unseen structure dominating their mass, may be altered by their environment, leading to slightly different dynamical behavior. Environmental influence also shapes morphology. Many void galaxies are irregular or late-type spirals with loose structures, patchy star-forming regions, and extended gas envelopes. Without the gravitational harassment common in galaxy groups or clusters, these galaxies maintain fragile features that would otherwise be disrupted. Long arms remain intact, faint outer disks survive, gas reservoirs stay extended and undisturbed. Even bars and spiral patterns can evolve differently when the galaxy lives in a near-perfect cosmic solitude. Another factor contributing to the slower evolution of void galaxies is the lack of major mergers. In average or high-density environments, mergers play a central role in transforming galaxy structure, building bulges, igniting starbursts, and reshaping disks. In voids, major mergers are exceedingly rare. A galaxy may never experience one, or only encounter small satellite systems that barely affect its overall structure. The result is a smoother, more gradual evolutionary path. Star formation continues at a steady rate, gas is consumed slowly, and morphology remains relatively stable across hundreds of millions of years. Observationally, studying these galaxies often requires different strategies. They are faint, spread across enormous distances, and sparsely distributed. Radio telescopes are crucial for detecting their HI content. Optical data reveal their stellar populations and chemical composition. Ultraviolet observations help trace recent star formation. Each wavelength tells part of the story. Combined, they reveal galaxies that feel like remnants of an earlier era, modern objects with ancient characteristics. These galaxies are not frozen in time, but they evolve at a pace and in a manner distinct from their counterparts in more populated environments. Their slow chemical enrichment offers insight into how the first galaxies might have behaved before the cosmic web became as structured as it is today. Their gas-rich nature helps test theories of star formation under minimal external pressure. Their dynamical oddities challenge models that assume galaxies evolve mostly through interactions and mergers. And their very presence inside the Boötes Void illustrates how structure can emerge even in the universe's emptiest expanses. As telescopes improve and surveys expand, more of these rare systems come into view. Each new detection adds to the mosaic, refining our understanding of how isolation shapes the life of a galaxy. The Boötes Void, despite being one of the most desolate regions in the cosmic landscape, offers a surprising abundance of scientific insights simply through the few galaxies that inhabit it, tiny beacons of light in a vast and quiet ocean. To understand why the Boötes Void exists at all, we have to return to the earliest whispers of structure in the universe, long before stars formed, before galaxies swirled into existence, before even hydrogen atoms had cooled enough to settle into being. In that primordial era, the universe was governed by a faint pattern imprinted during inflation, scattered through the hot, dense plasma in the form of tiny quantum fluctuations. These fluctuations were unimaginably small disturbances in density, ripples in the early cosmic sea, but inflation stretched them across astronomical distances, turning microscopic randomness into macroscopic structure. These fluctuations weren't just curiosities, they were the seeds from which everything later grew. Slightly denser regions contained just enough extra mass to begin slowing down relative to their surroundings, letting gravity take hold. Slightly emptier regions expanded a little faster, gradually falling behind the cosmic average. A patch that began lighter would become lighter still, its matter pulled away by surrounding overdensities. Over hundreds of millions of years, the contrast between dense regions and empty regions intensified, laying the groundwork for the universe's grand web-like architecture. This process unfolds naturally within the lambda CDM model, the standard cosmological framework that combines cold, dark matter, CDM, and dark energy, represented by lambda, the cosmological constant. In lambda CDM, dark matter provides most of the gravitational pull, clustering into halos that later gather gas and form galaxies. Meanwhile, dark energy drives the accelerated expansion of the universe, subtly shaping how structures grow and drift apart. In overdense regions, dark matter collapses into knots and filaments. In underdense regions, dark matter flows outward, thinning the interior even further. Supervoids are simply the extreme end of this process, the deepest troughs in the initial density landscape. In a typical density field, most voids start small, only a few million light-years across. They grow through a combination of expansion and evacuation. Matter slowly drains outward as the region's internal gravity weakens. The less matter a void contains, the faster it expands relative to the rest of the universe. This causes voids to inflate like rising bubbles in a cosmic dough. But the truly enormous voids, like Boötes, form through a different mechanism as well, void merging. The universe's structure resembles a vast foam. At early times, countless small, low-density patches pepper space. As the universe expands, neighbouring voids begin to drift toward each other, their walls thinning, until eventually the barriers separating them collapse. Two small voids become one larger void. Then that void merges with another. Over billions of years, this hierarchical growth, small voids combining into larger ones, creates supervoids hundreds of millions of light years across. The Boötes Void likely formed from the merger of many smaller voids, each born from a distinct dip in the primordial density field. In simulations, this process is easy to visualize. The early universe resembles a gently rippling surface with peaks and valleys. Over time, the valleys deepen and widen. Matter flows downhill toward the peaks, draining from the lowlands and enhancing their emptiness. Eventually, the valleys touch, merge, and form a connected network of vast, underdense basins. The Boötes Void is simply one of the largest of these basins, a gargantuan hollow that marks where the early fluctuations aligned in a way that promoted deep underdensity. The key driver behind this evolution is the behavior of dark matter. Dark matter dominates the gravitational landscape, shaping everything from galaxy formation to the growth of cosmic voids. In overdense regions, dark matter collapses, forming halos, filaments, and superclusters. In underdense regions, the opposite occurs. Dark matter flows outward, leaving behind a smooth, thin distribution that lacks the gravitational clumping needed to form structure. This evacuation is subtle but relentless. With each passing billion years, more dark matter migrates toward nearby peaks in the density field, feeding the formation of massive clusters and superclusters while leaving void interiors increasingly barren. What remains inside a void is mostly the faintest background of matter, rare streams of dark matter, a few scattered hydrogen clouds, and the occasional galaxy that managed to form despite the inhospitable conditions. These lonely galaxies are the survivors of a gravitational lottery, forming in places where small pockets of dark matter were just dense enough to seed stars. Everywhere else, the evacuation process left the void interior too thin to collapse. Contrast this with the behavior of overdense regions. In crowded zones, dark matter collapses from every direction, creating filaments, long thread-like structures where matter flows along gravitational channels. Where filaments intersect, matter piles up into clusters. Multiple clusters linked together form superclusters, enormous collections of galaxies that shine like cosmic cities strung along the highways of the universe. These bright structures form the walls and edges around voids, outlining their shapes like the ribs of a hollow sphere. The Boötes Void sits encased in such a network of bright structures. The galaxies at its periphery mark where dark matter accumulated over time. These walls are not smooth or uniform. They are stitched together from filaments and sheets, the result of billions of years of gravitational sculpting. Simulations show that when dark matter flows outward from void interiors, it doesn't disperse evenly. Instead, it streams along the paths of least resistance until it reaches neighboring filaments. This continuous flow thickens the boundaries of the void, sharpening its contrast even as the interior grows more dilute. Thinking of voids and overdense regions together creates a clearer picture. The universe is not a random scattering of matter, nor is it a smooth soup. It is an intricate balance of competing tendencies. Where matter pools, it intensifies. Where matter is lacking, emptiness magnifies itself. Gravity, left to organize the cosmos over billions of years, accentuates both extremes. Clusters become richer, voids become emptier, and the cosmic web stretches between them like a vast interconnected skeleton of structure. This interplay creates the hierarchy of voids that we observe. Small voids fill the spaces between nearby filaments. Medium voids sit between larger walls. And supervoids, like Boötes, span enormous regions where initial conditions favoured a deep underdensity from the start. The pattern resembles nested bubbles, each shaped by the density fluctuations imprinted at the dawn of time. Supervoids grow differently from halos and clusters. Halos collapse inward. Voids expand outward. Halos fragment into smaller systems. Voids merge into larger hollows. Halos heat up and form stars. Voids cool down and become dominated by dark energy's influence. And while halos are complex, chaotic, and highly non-linear, voids remain comparatively simple, quiet spaces where the expansion of the universe proceeds with minimal interference. The simplicity of voids makes them powerful scientific tools. They are shaped mostly by expansion, dark matter evacuation, and the initial density field, rather than by the messy physics of feedback, star formation, and mergers. The Boötes Void is not an exotic anomaly. It is the clean expression of these principles on a monumental scale, the product of gravity's long and patient work on the deepest troughs of the cosmic landscape. Inside a cosmic void, the physics of space behaves differently, not because new laws apply, but because familiar laws unfold under extreme conditions. A void is a place where the rules of gravity become gentler, where the tug of matter is weaker, and where the expansion of the universe stretches space with slightly fewer obstacles. The emptier the region, the more freely it grows. This simple principle, gravity's dependence on mass, creates a striking effect. Void interiors expand faster than the rest of the cosmos. The reason is rooted in gravitational pull. In regions filled with galaxies, clusters, and dark matter, gravity acts like a brake on the expansion of space. These dense areas resist the stretching of the universe, slowing it slightly. But inside a void, with much less matter to counter the cosmic expansion, there is barely anything pulling inward. The result is a kind of gravitational lightness. Space itself accelerates outward, expanding a little more rapidly than the cosmic average. Over billions of years, that difference compounds, subtly but relentlessly enlarging the void until it becomes a vast, balloon-like cavity surrounded by denser walls. This differential expansion creates one of the signature features of void dynamics, peculiar velocities. Peculiar velocity refers to the motion of galaxies relative to the smooth expansion of the universe, the extra push over and above the cosmic flow caused by local gravitational forces. Near the edges of a void, galaxies often exhibit outward peculiar velocities, as if being gently pushed away from the center. It's not a literal push, of course, but a consequence of gravity working unevenly. The galaxies just outside the void sit in regions that are slightly denser, where gravity is stronger. From their perspective, the weaker pull inside the void results in a net outward acceleration. If you picture the cosmic web as a network of crowded intersections and empty streets, a void is the quietest street of all. Matter naturally drifts toward the intersections, toward clusters and filaments, leaving the empty roads emptier still. Over time, gas, dark matter, and even galaxies flow outward toward the surrounding structures. This process is not rapid. It unfolds across billions of years, but it creates a steady, measurable outflow pattern. Galaxies in the interior of a void slowly migrate toward the boundary, while galaxies near the boundary move along gravitational gradients into the filaments beyond. This motion gives voids an almost atmospheric behavior. Just as air flows from high pressure to low pressure on Earth, matter flows from underdense regions to overdense ones in the universe. The analogy isn't perfect. Cosmic matter isn't a fluid in the classical sense, but the large-scale pattern resembles a slow cosmic wind. Inside the Boötes Void, that wind has had hundreds of millions of years to operate, gradually evacuating mass and sharpening the contrast between its hollow center and its bright, crowded perimeter. As matter streams outward, the void itself grows, not just because the universe expands, but because the boundaries evolve. The walls surrounding voids thicken as they collect the material that has drifted out of the interior. This creates a visible edge when plotted in redshift space, a transition from near emptiness to sudden structure. In some surveys, this edge looks like a faint shell of galaxies. In others, it resembles a network of filaments forming the ribs around a hollow sphere. The Boötes Void's surrounding structures reveal these dynamics clearly, with bright arcs and tendrils marking where matter has accumulated. This outward flow has an interesting gravitational consequence, one that cosmologists describe with an evocative term: repulsion-like dynamics. It's not that voids literally repel matter. Gravity never pushes, only pulls. But because matter is drawn more strongly toward denser regions, the relative effect is that galaxies appear to be pushed away from void centers. Astronomers sometimes compare the behavior of voids to buoyancy. A galaxy sitting near the edge of a void is pulled toward a nearby filament in the same way that an air bubble rises toward the surface of water. The bubble isn't actively pushing, but the environment around it creates the appearance of motion. This kind of motion becomes especially important when considering the large-scale flow of galaxies in our cosmic neighborhood. For decades, astronomers puzzled over the peculiar velocities of galaxies near the Milky Way. Some galaxies move towards certain regions of the sky faster than expected, while others drift away with surprising speed. When these velocities were mapped, they didn't align perfectly with the gravitational pull of nearby overdensities like the Shapley concentration, a massive supercluster far beyond the Virgo cluster. Something else seemed to be influencing the flow. That something turned out to be a void, a very large, underdense region exerting a subtle but significant influence on galaxy motions. This came to be known as the dipole repeller, a vast void whose gravitational absence creates a flow pattern in the opposite direction of a major attractor. In other words, galaxies in our region are not only pulled toward Shapley, they are also effectively pushed away from the dipole repeller. Again, gravity is not doing any pushing. The motion arises from the competing attractions of dense regions and the relative weakness of attraction inside the void. The interplay between a major attractor and a major void can create a dipolar flow, where galaxies stream toward one direction while flowing away from another. This contrast helps explain the large-scale peculiar motions in our part of the universe, giving astronomers a clearer sense of how voids and overdensities shape cosmic structure. The Shapley attractor and the dipole repeller illustrate the two ends of gravitational behavior on cosmic scales: immense mass pulling galaxies inward, and vast underdensity allowing galaxies to drift outward with ease. The same principles apply to supervoids like the Boötes Void. Its size and depth influence the movement of galaxies around it, contributing to the flow of matter along nearby filaments. The surrounding structures act as both channels and destinations for this flow. In cosmological simulations, voids appear as expanding cavities, pushing into neighboring regions and slowly altering the shape of the cosmic web. Each void interacts with others around it, sometimes squeezing them, sometimes merging, sometimes shifting the direction of cosmic flows. Another aspect of void dynamics is the behavior of dark energy. In the lambda CDM framework, dark energy accelerates the expansion of the universe uniformly, but its effects are more visible in voids, where there is less matter to counteract it. This means voids are the regions where cosmic acceleration expresses itself most cleanly. In dense environments, gravity fights back, slowing the expansion locally. In voids, dark energy wins with almost no resistance. This creates a subtle enhancement of expansion, one that contributes to the growth of voids over time and amplifies the peculiar velocities at their edges. One interesting observational feature linked to void dynamics is the distortion of void shapes in redshift space. Because galaxies inside voids have peculiar velocities oriented outward, their redshift distances can appear slightly larger than expected. This creates an elongation effect when plotted in 3 dimensions. While not dramatic, the distortion is measurable, and astronomers use it to study the expansion rate and gravitational influences inside voids. These distortions contain clues about the density contrast, the outflow speed, and even hints of how dark energy behaves on large scales. All these effects combine to give voids a kind of quiet dynamism. They may look static in diagrams, but they are constantly changing. Their interiors thin out, their edges thicken. Their shapes stretch and shift under the influence of nearby structures, and their interactions with dense regions create a complex flow of galaxies across tens or hundreds of millions of light-years. The Boötes Void is not just an empty place. It is an evolving cavity sculpted by cosmic expansion, dark matter evacuation, and gravitational interplay with surrounding filaments. Watching void dynamics unfold in simulations feels almost like observing a slow cosmic ballet. Galaxies drift outward along gentle gradients, filaments bend and tighten, boundaries swell and adjust. Over immense timescales, small voids merge into larger ones. Larger voids expand into supervoids, and all the while, dark energy pushes the universe outward, subtly accelerating the growth of its most empty regions. In this choreography, voids play a vital role in balancing the overall structure of the cosmos. They are the spaces that allow filaments to stretch and clusters to gather. They are the regions where cosmic expansion reveals itself most plainly. They shape the flow of galaxies, the formation of structures, and the geometry of space on the largest scales. The Boötes Void, with its vast size and remarkable underdensity, stands as one of the clearest expressions of this quiet but powerful dynamic, an immense hollow that grows not through motion or force, but through the absence of mass and the relentless expansion of the universe itself. Voids are more than empty regions of space. They are precision instruments, natural laboratories where the fundamental physics of the universe becomes visible in its most distilled form. In the crowded hubs of the cosmic web, galaxies, gas, and dark matter swirl together in a complicated blend of interactions. Feedback, mergers, turbulence, and dense gravitational fields blur the signals researchers try to measure, but inside a void, almost all of that noise falls away. There, in the quiet, the universe reveals some of its most subtle tendencies with surprising clarity. This is why cosmologists have come to value voids so highly, especially supervoids like the one in Boötes. They don't just represent emptiness, they provide a careful testbed for studying dark energy, gravity, cosmic expansion, and the geometry of space. Their near-linear behavior makes them cleaner than clusters, calmer than filaments, and far simpler than the chaotic centers of galaxies. A void is, in some ways, the universe stripped down to its essentials. One of the most important areas where voids have become powerful tools is the study of dark energy, the mysterious component of the universe that drives its accelerated expansion. Dark energy is often described using a parameter called W, the equation of state parameter. It relates dark energy's pressure to its energy density. If W equals -1, dark energy behaves like a cosmological constant, perfectly uniform in space and time. If W differs from -1, even slightly, it could indicate that dark energy changes over time or arises from exotic physics beyond the standard model of cosmology. Measuring W is extraordinarily difficult. Dense environments introduce complexities that mask dark energy's influence. But in voids, dark energy exerts its effects with fewer obstacles. These regions expand more freely than the average universe because their internal gravitational pull is so weak. The rate at which a void stretches, the shape it takes, and the peculiar velocities of galaxies around its edges all carry fingerprints of dark energy's behavior. Astronomers analyze these patterns using surveys that map the distribution of voids across cosmic time. By comparing void sizes at different epochs, they can infer how the expansion rate has changed and whether W remains constant. Studies show that voids grow noticeably faster in models where W deviates from -1 because even small deviations affect how rapidly underdense regions thin out. The Boötes Void, along with thousands of smaller voids catalogued in surveys such as SDSS and DESI, provides an enormous dataset for these kinds of tests. Each void, with its growth rate and geometry, contributes a small but important piece to the puzzle of how dark energy behaves. Voids are equally valuable for examining modified gravity theories, alternatives to general relativity that attempt to explain cosmic acceleration without invoking dark energy. Many of these theories introduce changes in how gravity behaves on large scales. Some strengthen it, some weaken it, some add extra fields or forces that act only in low-density regions. Dense regions can hide these modifications because high matter density screens new forces, making them difficult to detect. Voids, however, lie below the threshold where screening mechanisms are effective. In these open, weightless expanses, any deviation from Einstein's theory stands out more sharply. One approach to testing gravity in voids involves studying their density profiles, how matter scatters from the center outward. In standard gravity, simulations predict specific profiles for voids of different sizes and ages. Modified gravity models often alter these curves, changing the speed at which matter flows outward or the thickness of void boundaries. Another approach uses galaxy motions. Peculiar velocities around void edges follow predictable patterns in general relativity. Deviations from these patterns suggest the influence of additional long-range forces. Weak gravitational lensing provides a third window into void physics. While voids contain too little mass to lens strongly, the subtle distortions they imprint on background galaxies reveal how space itself stretches around them. These distortions, too faint to see with the naked eye, add another layer of information about how gravity shapes the universe in its emptiest places. The fact that voids magnify the effects of modified gravity while suppressing non-linear complications makes them one of the most promising probes for testing the foundations of gravitational physics. Another elegant technique for studying cosmology through voids is the Alcock-Pogzinski test, a geometric method that examines the apparent shape of objects in the universe. The test rests on a simple idea. If the universe is expanding uniformly and distances scale the same way along every direction, a population of spherical objects should appear spherical on average. If the objects look stretched or squashed along the line of sight, it indicates that the assumed cosmological parameters, like the expansion rate or the curvature of space, might be incorrect. Voids are almost perfect candidates for this test. Even though individual voids are often irregular, the statistical average of many voids should approach spherical symmetry. By measuring thousands of voids in different redshift ranges and comparing their shapes, astronomers can constrain cosmological parameters with remarkable precision. Any anisotropy, any consistent stretching caused by incorrect assumptions about distances, time or space, shows up directly in the void shape distribution. Applying the Alcock-Pogzinski test to voids has become a major area of research in large redshift surveys. The advantage is that void shapes depend primarily on geometry, not on the complex astrophysical processes that affect galaxies or clusters. With datasets like DESI, which aim to collect tens of millions of galaxy redshifts, the test gains even more power. Voids become quiet geometric rulers, measuring the shape of the universe with a precision few other tools can match. One of the most fascinating observational effects involving voids, and one that connects them directly to the early universe, is the integrated Sachs-Wolf (ISW) effect. The ISW effect occurs when photons from the cosmic microwave background pass through evolving gravitational potentials. In simple terms, if a region of space changes while light is travelling through it, the energy of that light can be slightly altered. In an unchanging universe, the gravitational potentials of voids and clusters would remain static, and photons entering and exiting them would cancel any energy shifts. But in a universe where expansion accelerates, thanks to dark energy, the potential wells and hills slowly fade. This fading creates a tiny mismatch in the photon's energy before and after passing through the region. For voids, the effect works like this. As a CMB photon crosses an underdense region, it gains a little energy falling into the shallow potential, but because the potential weakens during the crossing due to the accelerated expansion, it doesn't lose as much energy climbing back out. The result is a photon that emerges slightly hotter. The temperature shift is minuscule, only a few microkelvin, but across many voids the effect becomes statistically detectable. Observing the ISW effect through voids provides another way to probe dark energy. If dark energy were weaker or absent, the effect would disappear. If its equation of state differed from -1, the strength and pattern of the signal would shift accordingly. Measurements of the ISW effect across large void samples help test these possibilities, offering one of the rare direct observational windows into the impact of dark energy on the growth of structure. Supervoids like the Boötes Void are especially interesting in this context. Their enormous size makes them prime candidates for producing stronger ISW signatures. Some studies suggest that extreme voids might leave imprints visible even in individual cases, though the statistical debate continues. Whether or not these imprints are strong enough to isolate clearly, the combination of void catalogues with CMB maps remains one of the most sensitive probes of how cosmic expansion changes over time. The interplay of these observational techniques, geometric tests, velocity measurements, lensing, density profiles, and CMB interactions turns voids into multi-purpose cosmological tools. Each method isolates a different aspect of the universe's expansion, structure, or gravity. Together, they offer a cross-checking network of constraints, allowing cosmologists to refine models with increasing accuracy. In dense regions, astrophysical complications create uncertainties, but in voids, the universe behaves closer to its simplest theoretical form, letting physics reveal itself with fewer interfering factors. As redshift surveys reach deeper into space and gather more galaxies, the power of void-based cosmology continues to grow. Voids bring subtle signals into focus, whether from dark energy's steady push, gravity's quiet pull, or the faint shadows cast on the microwave background. They show how emptiness, far from being irrelevant, becomes a lens through which the most elusive features of the cosmos can be observed with extraordinary clarity. Whenever the universe presents something enormous, unusual, or visually dramatic, speculation tends to fill the silence before science arrives with an explanation. The Boötes Void is no exception. When astronomers first revealed a spherical region hundreds of millions of light-years wide with only a few dozen galaxies inside it, the public imagination immediately ignited. Headlines called it a black spot on the universe. Some described it as a cosmic cavity so empty it felt unnatural. A few went further, proposing ideas that sit halfway between science and science fiction. And whenever the topic of large voids arises, someone, somewhere, brings up alien megastructures. Large-scale megastructures, especially the classic Dyson sphere concept, tend to dominate discussions about advanced civilizations. A Dyson sphere is a hypothetical structure built around a star to capture its entire energy output. Scaling that idea up, some wondered whether a galaxy-spanning or even void-spanning engineering project could create the kind of emptiness seen in places like the Boötes Void. It's not hard to see why the question gets asked. A void, hundreds of millions of light-years across, looks almost like a region that has been cleared, and humans have a long history of projecting engineering solutions onto cosmic landscapes. But the first problem with this idea is simple physics. The energy required to remove galaxies, or even stars, from such a region is beyond astronomical. The gravitational binding energy of a galaxy is so enormous that even harvesting the output of every star in that galaxy for the age of the universe would barely budge it. A supervoid contains not just a few galaxies, but, if filled to normal density, many thousands of them. The amount of work required to push that matter outwards and leave behind a cleanly evacuated sphere is beyond anything achievable by any known physical process that doesn't simply involve letting gravity evolve normally. Another issue is that the distribution of galaxies inside the Boötes Void isn't consistent with removal. It's not uniformly empty. It has subvoids, filaments, and a faint internal structure that matches what simulations predict for naturally formed hollows. If an engineered void were carved out, one would expect cleaner edges or a more deliberate geometry, a kind of sculpted emptiness. The actual void looks nothing like that. It resembles the underlying density fluctuations predicted by lambda CDM, not a structure shaped by external intent. The alien megastructure idea runs into further trouble when compared with the cosmic microwave background. If galaxies had somehow been removed or dismantled, the gravitational potential of the region would have changed dramatically over time. That change would leave a clear imprint on the CMB, far stronger than the tiny signatures associated with the integrated Sachs-Wolf effect. No such imprint is observed. The Boötes Void aligns with the gentle, smooth variations expected from standard cosmic evolution, not from catastrophic rearrangement. That brings us to the second speculation that sometimes circulates, the idea of an engineered void created by large-scale manipulation of matter. This idea usually takes a step back from megastructures and imagines something like dark matter engineering, gravity control, or large-scale spatial clearing. Yet even these more subtle speculations falter for similar reasons. Voids do not have features that resemble engineered systems. Their density profiles match the predictions of gravitational evacuation. Their shapes align with the patterns expected from merged underdensities. Their boundaries are fuzzy, irregular, and sculpted by surrounding filaments, not crisp or symmetric. Engineered structures tend to have signatures of intention, symmetry, efficiency, sharp transitions, or grids of some sort. The Boötes Void has none of those. Every aspect of its structure can be explained by the slow, steady amplification of initial fluctuations in the early universe. Lambda CDM simulations routinely produce voids of comparable size. The Boötes Void may be striking, but it is not anomalous. It is simply one of the largest examples in our cosmic neighbourhood, notable not because it is inexplicable, but because it is rare enough to draw the eye. Large voids also spark speculation when compared to other enigmatic cosmic features, such as the Eridanus supervoid, often discussed in connection with the CMB cold spot. The cold spot is a region on the cosmic microwave background map that appears slightly cooler than its surroundings. Some studies have suggested that a very large void along the line of sight might cause a stronger than usual ISW effect, cooling the CMB photons more than expected. While not universally accepted, this hypothesis propelled voids into the spotlight as potential explanations for deep anomalies. The Eridanus region itself contains a significant underdensity, but its size and depth remain subjects of study. Some estimates suggest a void approximately 200 to 300 million light-years across, while others argue that the region's complexity makes it difficult to characterize with a single void model. The cold spot might be partly influenced by such a structure, but the evidence is not clear-cut. Alternative explanations range from statistical flukes to more exotic ideas, though the simplest interpretation remains that the cold spot is just a rare but natural fluctuation in the CMB. These debates often lead to comparisons with the Boötes Void. If the cold spot sparked wild ideas about cosmic anomalies, why doesn't Boötes do the same? After all, the Boötes Void is larger, cleaner, and more easily mapped. The difference lies in context. The cold spot appears in the CMB, the oldest light in the universe, making any anomaly feel far more fundamental. A void affecting the CMB would influence photons from 13.8 billion years ago, suggesting a deep cosmological significance. Meanwhile, the Boötes Void affects the present-day distribution of galaxies, a much more familiar and better understood realm of cosmology. What the Boötes Void does show, when compared to more speculative structures, is how consistent void behavior is within lambda CDM, the standard cosmological model. Lambda CDM predicts a broad distribution of void sizes. Most voids are small, but supervoids of hundreds of millions of light-years, while uncommon, are not surprising. Simulations regularly produce voids of comparable size. Their density contrasts, substructure, and growth histories align with theoretical expectations. The Boötes Void fits comfortably within this distribution. Large, yes, but statistically acceptable. Simulations also predict that the largest voids will be irregular, shaped by the merging of multiple smaller voids. They will have thin internal filaments, remain slightly asymmetric, and show gradual density transitions rather than sharp edges. All of these characteristics match what surveys have observed in Boötes. The void's presence is therefore not evidence of anomalous physics, but an affirmation of how voids behave in lambda CDM, a successful prediction, not a contradiction. Moreover, the Boötes Void is not the largest known supervoid. Other structures, such as the KBC void and the local void, are often cited as having comparable or even greater extents in certain dimensions. The KBC void, for example, is a very large underdensity that may span nearly 1 billion light-years. Its implications for local measurements of expansion have sparked scientific discussions, but none suggest the presence of engineered or exotic forces. The existence of these structures reinforces the understanding that supervoids are simply part of the cosmic landscape. Even the most unusual features of voids, such as the faint strings of galaxies inside them, reflect natural processes. Voids do not form as perfect vacuums. They are shaped by the initial conditions of the universe and the interactions among surrounding filaments. The galaxies inside Boötes, scattered, isolated, metal poor, fit the profile expected for objects that formed in the shallow gravitational wells of an underdense region. Their presence is not evidence of artificial intervention, but of the universe's tendency to produce structure even in its emptiest places. Speculation, whether about megastructures or engineered voids, tends to arise where the universe presents something visually dramatic. But dramatic is not the same as unnatural. The Boötes Void is dramatic because it is large, not because it is anomalous. From the standpoint of modern cosmology, it represents an expected, though extreme, outcome of the growth of structure. The physics that governs voids, dark matter evacuation, gravitational expansion, merging under densities, explains its properties without stretching known laws. In many ways, the Boötes Void serves as a reminder of how the simplest processes in the universe, given enough time, can produce structures that seem almost uncanny. The quiet growth of emptiness, the slow drift of matter outward, and the gentle amplification of small differences have sculpted a hollow so vast that its dimensions strain human intuition. But the void needs no extraordinary explanation. Its existence emerges directly from the physics that shaped everything else: the filaments, the clusters, the galaxies, and the fabric of space. Voids do not need engineers to exist. Gravity is enough. The early universe, with its tiny imperfections, provided the blueprint. Billions of years of cosmic expansion did the rest. The Boötes Void often earns its reputation as one of the most dramatic hollows in the nearby universe, but it is only one member of a larger family of vast underdense regions. The cosmic web is a patchwork of high-density nodes, clusters, filaments, walls, and the vast expanses between them. When seen in simulations, these voids form a honeycomb of interconnected cavities, some small and sharply defined, others sprawling and diffuse. The Boötes Void stands out because of its emptiness and clean structure, but on the grand scale, it is part of a population that reaches from modest hollows tens of millions of light-years across to gargantuan basins stretching nearly 1 billion. The nearest large void to the Milky Way is simply called the local void. It lies adjacent to the region of space where our galaxy resides and directly influences the movement of the Milky Way and its neighbours. The local void is not as cleanly spherical as Boötes, nor as empty, but it exerts a noticeable gravitational effect. Because it is underdense, galaxies on its boundary appear to move outward relative to its centre. The Milky Way, sitting near that boundary, participates in this motion, drifting away from the local void even as it falls toward larger gravitational attractors. The local void's structure highlights an important feature of many voids. Their boundaries are not solid rims but permeable, shifting regions shaped by the mass distribution around them. Unlike Boötes, which appears more self-contained, the local void blends into adjacent underdensities and filaments with softer transitions. Its full extent is difficult to map precisely because much of it lies in the zone of avoidance, the part of the sky obscured by the Milky Way's stars and dust. Even so, reconstructions of the local cosmic flow strongly suggest that the local void spans at least 150 million light-years in one direction, though its true volume may be considerably larger. Further from home lies one of the most debated and intriguing structures in modern cosmology, the KBC Void, named after Keenan, Barger and Cowie, who proposed that the region surrounding the Milky Way is part of a much larger underdensity, possibly extending up to 1 billion light-years in diameter. The KBC Void is not an empty sphere, but a large-scale underdense region where galaxy counts appear lower than the cosmic average across a tremendous expanse. This claimed size places it among the largest underdensities ever suggested. Its significance arises not only from its scale, but from the question of whether such a structure could influence local measurements of the Hubble constant. The ongoing tension between different methods of measuring the universe's expansion rate. If the Milky Way happens to sit inside a slight underdensity, the local expansion rate could appear higher than the global average. Some researchers argue that the KBC void provides just enough underdensity to produce this effect, potentially softening the current discrepancy. Others counter that the void is not deep enough, large enough or uniform enough to have such a dramatic impact. Regardless of that debate, the KBC structure, however precisely one defines it, demonstrates that supervoids in the hundreds of millions of light-years range are not unique to Boötes. They emerge naturally within lambda CDM's predicted distribution of fluctuations, though the upper end of the scale becomes increasingly rare. Another important example is the Sculptor Void, a sizable underdense region that lies beside the Sculptor supercluster. The Sculptor Void shares some structural characteristics with Boötes, an interior that appears sparsely populated, a boundary marked by bright galaxy distributions, but it is stitched into a more complex environment. Rather than sitting in relative isolation as Boötes does, the Sculptor Void is embedded among several nearby filaments that thread around and through it. This makes its shape more irregular and its dynamics more influenced by adjacent overdense structures. The Sculptor Void also has significance in understanding the motion of the local group. Combined with the local void and other nearby underdensities, it forms part of a larger topological network of voids shaping the flow of galaxies in our region. These voids are not isolated spheres floating in an empty sea. They link together in a patchwork, steering cosmic flows much like valleys guiding water in a mountain landscape. Beyond these familiar supervoids lies a region that often captures popular attention due to its extraordinary scale, the Hercules Corona Borealis Great Wall and its surrounding structure. This feature is usually discussed as an overdense region, an immense wall of galaxies spanning several billion light-years, but large overdense structures often form beside equally large underdensities. The spaces between the filaments of the Hercules Corona Borealis region include some of the most extended low-density areas ever identified, though they are difficult to characterize precisely because of their scale and the challenges of mapping such distant structures with high fidelity. In extremely large-scale surveys, these enormous void-like regions appear connected, stretched between the nodes of the cosmic web. Unlike the Boötes Void, which sits relatively isolated and well-defined, these far-flung voids are diffuse, merging into each other without clean boundaries. Their edges are shaped by the filaments of the Great Wall and other surrounding galaxy overdensities, making them part of an immense, evolving complex of structure. The diversity among these voids raises an important question. Why do some voids reach a few tens of millions of light-years, while others approach a billion? The answer lies in statistics. The universe's initial density field, imprinted shortly after the Big Bang, was random but followed a well-defined distribution governed by inflation. From that distribution, one can predict how common underdensities of different depths and sizes should be. Small voids occur frequently. Medium voids occur less often. Supervoids, those hundreds of millions of light-years across, appear rarely, but not unexpectedly. A void like Boötes, while extreme, falls within the tail of this statistical distribution. The largest voids, such as those associated with the KBC region, lie near the limits of this tail. Their existence is not an anomaly. It is a natural consequence of sampling a huge cosmic volume. The universe is big enough that even rare structures have room to form. Supervoids represent the deepest troughs in the cosmic density landscape, just as superclusters represent the highest peaks. Both arise from the same primordial fluctuations amplified over billions of years by gravity and cosmic expansion. The statistical distribution also predicts that voids will often merge into larger complexes, especially at late cosmic times. This tendency explains why some voids, like those near the Hercules Corona Borealis region, appear connected or blended. It also explains why the Boötes Void contains internal subvoids. Smaller hollows left behind after merging processes softened the boundaries between them. Each void, no matter how large or small, reveals part of the cosmic story. The local void shows how underdensities influence galaxy flows close to home. The sculptor void demonstrates how voids fit into the complex topology of surrounding filaments. The KBC region pushes the upper limits of void size and offers a testing ground for cosmological parameters. And the Boötes Void, balanced among them, serves as one of the clearest, most dramatic examples of just how empty the universe can become when gravity and expansion shape the underlying density field into extremes. These voids illustrate the full hierarchy of cosmic hollows, from modest gaps to immense basins, all formed by the same simple rules acting across staggering scales. Picture yourself drifting inside the Boötes Void, not metaphorically, but as if you were on board a small, silent spacecraft gliding through its centre. The darkness around you is not the same darkness you would see from the Milky Way. Here the universe feels stretched thin, almost translucent. The familiar canopy of stars is gone. In its place is a sky so sparse that entire minutes might pass before your eyes catch a single point of natural starlight. In this region, where roughly one galaxy occupies every 10 million cubic light-years, the night does not sparkle, it barely flickers. The few galaxies you do see appear as faint smudges, tiny isolated islets in an ocean of black. No thick clusters, no glowing bands, no dense knots of structure. Even the brightest galaxies inside the void, viewed from its centre, would look smaller and dimmer than the most distant objects visible from Earth. Their light has travelled for tens or hundreds of millions of years, attenuated by unimaginable distance long before it reaches you. In such conditions, starlight feels more like a rumour than an illumination. Travelling between these galaxies highlights the enormity of this environment. In a typical region of the cosmic web, galaxies might be separated by a few million light-years. Crossings between neighbours, while still immense by human standards, fall within cosmological norms. Inside the Boötes Void, those distances expand into something almost abstract. The nearest galaxy may lie 50 to 100 million light-years away. Even travelling at a respectable fraction of light speed would turn the journey into an epic crossing of cosmic emptiness. A spacecraft moving at 1% of light speed, already far beyond today's capabilities, would still require 5 billion years to traverse such a gap, and that assumes you aimed perfectly. A slight misalignment could send you gliding for ages without encountering anything but dust, plasma, and the faint glow of the cosmic microwave background. The medium through which you travel is nearly a vacuum. In the disk of the Milky Way, the interstellar medium contains roughly 1 atom per cubic centimetre, a surprisingly thin environment by everyday standards, but luminous and dense compared to the void. Here, the intergalactic medium density drops to around 10 to the -8 particles per cubic centimetre, 8 orders of magnitude lower than the space between stars in our galaxy. That means you could sweep a volume the size of a swimming pool and find almost nothing, perhaps a few stray atoms of hydrogen, drifting slowly under the influence of cosmic expansion. With so little matter around, your ship would encounter almost no collisions with particles, no measurable drag, no bursts of gas clouds or molecular filaments. Even the most sensitive detectors would register only a gentle whisper of baryonic presence. Dark matter is here, of course. Its invisible gravity shapes the void's overall structure, but it too is sparse compared to other regions. The gravitational landscape feels softened, as though the universe's fabric is thinned out. In such a place, familiar cosmic light sources give way to the more ancient, uniform glow of the cosmic microwave background. The CMB would dominate your sky, a faint, nearly perfect bath of microwave radiation at a temperature of about 2.7 Kelvin, spread evenly across every direction. In a galaxy, starlight overwhelms this background. Here, it becomes the primary illumination. Sensitive instruments would see the CMB as a smooth field, with only tiny temperature variations, a map of the early universe calmingly present in every direction. The ionizing background, driven mostly by distant quasars and galaxies far beyond the void's edge, still permeates this emptiness. High-energy photons stream through without resistance, unhindered by clouds of gas or dense regions of plasma. The ultraviolet and X-ray background is weak here, but not absent. It is simply unopposed. The few hydrogen atoms floating in the void spend most of their time ionized, stripped of electrons by radiation that travels freely across hundreds of millions of light years. This makes the void interior an almost fully ionized plasma, but at densities so low that even calling it plasma feels generous. If you look toward the boundary of the void, those faint walls where galaxies gather into filaments, you would see structure return slowly. The edges appear as lightly glowing arcs, barely visible to the naked eye but prominent through instruments. These walls do not shine through their own luminosity, they shine through contrast. After spending time in the deep interior, even a sparse filament containing a modest number of galaxies would feel like a brilliant ridge, a distant skyline marking the transition from emptiness to structure. As you continue drifting, you might tune your instruments to specific wavelengths. In optical light, the void yields almost nothing. In the ultraviolet, a faint background from faraway quasars. In radio wavelengths, you could search for HI emission, the familiar 21 centimetre, about 8.27 inches, line from neutral hydrogen. But in the heart of a supervoid, even this signal is barely present. Only a few rare galaxies emit detectable HI lines, and the path between them is so long that your detectors would spend most of their time listening to cosmic silence. At infrared wavelengths, you would pick up the collective glow from dust in distant galaxies, but it would be faint and diffuse. Across most of the spectrum, the void expresses itself not through presence, but through absence. The environment feels stripped to its essentials, a near-perfect laboratory for cosmic expansion, a window into the universe's most fundamental background signals, a place where time and distance dominate all other phenomena. Moving through this region offers a peculiar sense of isolation, even from a scientific perspective. Without nearby galaxies to distort gravitational measurements, the local expansion of space feels smoother, peculiar velocities are minimal. Gravity from distant filaments exerts only gentle, uniform pulls. Instruments designed to measure cosmic acceleration would find the void an ideal setting, with fewer non-linear complexities to obscure the signal. It's one of the few places where the expansion of the universe becomes almost palpable. If you cut the engines, your ship would drift endlessly, carried by the expansion of space. No stars would guide your path. No nearby planets would alter your course. The few galaxies inside the void would recede ever so slowly, not because of local motion, but because the space between you and them steadily stretches. The CMB would continue bathing your surroundings with perfect uniformity, and the silence, cosmic, physical, and absolute, would feel like a constant presence. In the Boötes Void, distance defines everything. Light takes millions of years to cross gaps so vast that galaxies appear as dust on the cosmic horizon. Matter is so thinly scattered that physics feels minimalist, and yet even here, the universe offers clues: hydrogen ions drifting through the dark, background radiation whispering of the Big Bang, faint structures at the borders reminding you that the cosmic web continues its vast architecture just beyond your reach. As the universe continues to expand, cosmic voids will become even more prominent. Their growth is driven by a simple imbalance. There is not enough matter inside them to counter the expansion of space. Gravity cannot pull inward where matter is scarce, but expansion acts everywhere. In regions like the Boötes Void, with density contrasts around -0.9, the expansion of the universe plays out almost without resistance. Over long stretches of cosmic time, this imbalance will widen the voids, thin their interiors further, and gradually push their boundaries outward. Dark energy accelerates this transformation. Today, it accounts for roughly 70% of the universe's total energy density, and its influence increases as space expands. In overdense regions, clusters, filaments, galaxy groups, gravity still competes. But inside voids, dark energy has almost no opposition. The geometry of space inside these hollows stretches a little faster than the cosmic average, amplifying their size. As billions of years pass, voids grow into one another, merging into larger, quieter expanses. Their walls become more pronounced as matter continues to flow outward, concentrating in the structures that outline the cosmic web. Far into the future, this trend will reshape the universe's large-scale appearance. Cosmologists often describe this as the void-dominated era, a phase where most of the universe's volume is made of emptiness rather than structure. Galaxies will remain in their filaments and clusters, but the regions between them, already vast, will grow so large that the connectedness of the cosmic web becomes harder to recognize. If the universe continues its current acceleration, these voids will expand until the isolated islands of structure are separated by jarring, unbridgeable distances. Filaments may thin, clusters may drift apart, and the shapes we now see in maps of the cosmic web may blur into a more fragmented landscape. The Boötes Void offers a preview of that distant future. Its interior already resembles the universe long after the scale of galaxy clustering becomes diluted by expansion. Sparse galaxies, gently receding boundaries, a near-uniform radiation field. These characteristics echo what cosmologists expect billions or trillions of years from now. Studying such a void today is like looking through a window into cosmic time, offering hints of how structure ceases to grow and how emptiness becomes the universe's dominant feature. This is why future telescopes are preparing to examine voids with increasing precision. Instruments designed for deep surveys excel not in crowded regions, but in the outskirts, along the faint edges, and within the quiet hollows. The Euclid mission, launched by the European Space Agency, is one of the most powerful tools for studying voids through weak gravitational lensing. Euclid will measure how the shapes of distant galaxies are subtly stretched by the mass distribution between observer and source. Even though voids contain little mass, they still influence light through their geometry. Mapping these distortions will reveal the density profiles of voids and test whether dark matter behaves as predicted across these vast underdense environments. The Rubin LSST, the legacy survey of space and time, will further transform void science. Its wide-field imaging will detect billions of galaxies, including the faintest, most sparsely distributed ones on the edges of voids. This unprecedented dataset will allow researchers to trace void boundaries with exquisite detail, identifying substructure and mapping the internal topography of underdense regions like never before. Rubin's temporal depth, revisiting the sky repeatedly over 10 years, will refine redshift measurements and improve void catalogues dramatically. Meanwhile, the SCAR, the Square Kilometre Array, will open another dimension of void research by mapping neutral hydrogen through the HI line at 21 centimetres, about 8.27 inches. Voids are ideal for HI studies because their galaxies are often gas-rich, chemically young, and minimally disturbed. SKA will detect these galaxies across huge distances, revealing their dynamics, gas content, and star formation histories in environments mostly untouched by interactions. It will also search for faint hydrogen signals within the void interiors themselves, probing the smooth intergalactic medium for any residual structure. Together, Euclid, Rubin LSST and SCAR form a triad of observational power, geometry, structure and gas physics, capable of dissecting supervoids from multiple angles. Each instrument reveals a different layer of the void, its mass distribution, its galaxy population, its gas content, its gravitational imprint, and its evolution over time. Through these detailed maps, cosmologists hope not only to refine the parameters that describe the universe today, but also to glimpse the trajectory of cosmic expansion far into the future. The Boötes Void occupies a special place in this research, not because it is unique, but because its clarity and emptiness make it a benchmark for comparison. Its smooth interior and relatively clean boundaries provide a template for understanding the growth and merging of voids. Its sparse galaxies offer ideal laboratories for low-density evolution, and its sheer size demonstrates that the universe is capable of producing extreme hollows without invoking exotic physics. The Boötes Void proves that gravity and the initial conditions set during inflation can sculpt spaces of astonishing emptiness. As cosmology enters an era of high-precision observation, supervoids like Boötes will serve as keys to answering fundamental questions about the universe's fate. They help reveal how dark energy shapes expansion, how the cosmic web evolves under acceleration, and how structure dissolves into isolation over unimaginable timescales. They are reminders that emptiness is not a passive feature of the universe. It is an active, dynamic component of its architecture. In the long view of cosmic history, voids expand, merge, and eventually dominate. The Boötes Void is simply an early chapter in that story. As you drift away from this vast hollow and its quiet lessons, let the scale of it settle gently into your thoughts. The universe grows through contrast, light and dark, mass and emptiness, and every void teaches us something about balance. Thank you for listening, and sleep well beneath the endless stars.